Hi, learning is easy. Just give your attention. Damped oscillations has three cases. You are watching one of the case. Let us learn all the three cases in detail. To learn about damped oscillations, let us take an example of spring mass system whose spring constant is K and a block of mass M, and spring is disturbed from its equilibrium position. Block of mass m will experience two forces. One force is acting due to the spring and another force is acting due to the air drag. And drag force is opposite to the velocity. For the scenario that we have taken, so there is a force kx acting leftwards and there is a drag force acting leftwards because velocity is rightwards, so that's why drag force is left. And here F net is nothing but a summation of spring force and drag force. And we can write F net force is equal to Ma, and Ma can be written as m into d square x by dt square, and spring force can be written as minus kx, and drag force can be written as minus Cp, where C is drag coefficient. When we rewrite this equation, we will get a differential equation which is md square x by dt square plus c into dx by dt plus kx is equal to 0. This differential equation is called second order linear homogeneous differential equation. I repeat, second order linear homogeneous differential equation. In the process of solving differential equation, we are coming across a discriminant, and discriminant here can have two real roots and two equal roots and two complex roots. So here we can clearly anticipate three different cases. So for d greater than discriminant greater than 0, the system will be in overdamped state. For discriminant equal to 0, the system will be in critically damped state. And for discriminant less than 0, the system is in underdamped state. Here whatever you're watching on the screen, so this is a simulation of damped oscillator, and we have here data inputs here. So mass value can vary, and here damping is nothing but a constant C, which is proportionality constant of drag force, and spring stiffness is nothing but a spring constant, and spring length and remaining are not that important, right? So now first let us talk about critically damped case. To have a critically damped case, so we have to have C square minus 4km has to be equal to 0. So C square minus 4km has to be equal to 0 means, so here C square is equal to 4km. Suppose if you take mass as a 1 and spring constant as a 4, and if you take C as 4, then we will be in critically damped state. So it's a very simple calculation, right? So here you can see C square minus 4km has to be equal to 0. So if you check just, so for the given values, discriminant will be 0. So we are now talking about critically damped case. Let us in a action. So there is no oscillation, right? So you can observe once again, there is no oscillation here. Okay, so critically damped case means there will not be any oscillation. Let us observe this one graphically too. So to observe graphically, right? So let us. I wish to have this thing. So I wish to have the graph in positive instead of negative. So I'm pulling it. I'm putting it here at 2, roughly at 2. Positive 2. Initial position is at x equal to 2, and that's it. So I will be right. Right. So this is the graph that you can see. There is no oscillation. So you can clearly observe. So initially at x equal to 2, and it is gradually coming to 0. So this is critically damped case. Now let us make d is equal to d is less than 0. If you make d less than 0, which is under damped case, right? So which is under damped case. How to make d less than 0? So let us go to the sim, right? Let us go to the sim, and here if we make d less than 4, so here the value of c, if we make here value of c less than 4, so the discriminant will be less than 0. So then you will go to the underdamped, you will fall under underdamped case. So I'm putting it as a value 2, so which is much lesser than 4, and let us see the graph how it will be. And here I wish to right. So again I'm starting with 2, position 2, and let us change the graph line so that we can differentiate between damped case critically, so that we can differentiate between critically damped case and underdamped case. So let us put it as a blue. So that's it. So I have set it as a blue. Let us play. Let's play it. So now you can see the oscillation. Okay, right. So oscillations happens when only in case of underdamped, which is when discriminant is less than 0. And now let us see what is how overdamped look like. Okay, so to have overdamping, so we need to uh, make discriminant is greater than 0, so which means value of C or damping here we have to make greater than 4. So which I am making it as a 8 here. I am doubling the value we have taken in case of critical depth. So now again we let us go for the graph, and again let us reset, right? And again let me reset this to 2, right? So that graph we can compare the graph, and let us name this graph. Let us change the color, so let us put it as a purple, and just let us play. So that's it. So purple one is overdamped, lime color are near to green, green line is critically damped, and blue one is underdamped. So oscillations happens only in underdamped case. Lastly, end note for this topic is memorize underdamped solution equation so that you can quickly answer the questions in exam.